Good afternoon. My name is John Lucas. I'm a lieutenant in the United States Navy. I'm going to be talking to you today about a new missile guidance algorithm to intercept ballistic missiles in their boost phase. Start off with the proliferation of intercontinental ballistic missiles has been accelerating for quite a few years now. North Korea is only one example of countries that are actively developing these programs. They've had some success in the last several years, including their current project is the Taepodong-2 missile, which is the one that I've chosen to model. It's a derivation of their Taepodong-1 missile, which was successfully put a satellite in orbit in 1998. This missile has a range of roughly 4,300 nautical miles, so it's capable of reaching the United States and carrying payloads sufficiently large to carry weapons of mass destruction as necessary. I've circled their missile test site that they've launched from. So when we talk about a missile in the boost phase, it's a very specific interval. The initial stages before it's while it's still boosting itself, overcoming gravity. Usually it's a multi-stage event. Breaks before the mid-course and then the terminal segment. Boost phase is generally very short, more often than not less than 5 minutes. So there's significant limitations on operating within this boost phase, but it's definitely something that needs to be incorporated into a layered defense, because if we can, even moderate success of stopping ballistic missiles in their boost phase translates to an extremely large success of stopping ballistic missiles in general. So today I'm going to talk to you about the missiles that I've chosen to model, their characteristics, the current guidance laws that we use in our tactical models. And I'm going to talk to you about the math that I've used to develop this algorithm, the geometry, the program specifics, and I'm going to show you a simulation of this model working. So as I mentioned, I modeled the Taepodong-2 missile, which is all the way on the far edge there. It's a 32-meter missile capable of 4,300 nautical miles. It carries about 750 to 1,000 kilograms. And the boost phase down at the bottom lasts for a total of 235 seconds. But as I'm going to talk about later, my time window is significantly shorter than that. Took all the data from James, from global security, from various unclassed sources, and built a mathematical model using standard ballistic missile equations from Zarchan, and developed what you see here. You can see that down the lower corner, my missile specifically does reach roughly 4,300 nautical miles, and that my accelerations achieve a velocity of just over 5, somewhere in the vicinity of 6 kilometers per second, which is the speeds necessary to achieve intercontinental ranges. And then down here in the corner, I've plotted the altitude versus time to show that the atmosphere of the planet Earth is only about 86 kilometers. And you see that even before the first and the second staging events, that the first staging event, we've already left the atmosphere. So and if I'm going to use an endo-atmospheric missile, I don't have until the end of the entire boost phase. I really only have until the end of the first stage of the boost phase. And then you add to that the time it takes to detect, track, authorize to launch, and actually engage the target. My time window becomes significantly short. But I'm not here to represent that particular aspect of this. I'm here to talk about the guidance law. So I've just assumed a 60-second delay between the time of the ballistic launch and the time of my interceptor launch, which leaves about 60 to 70 seconds left to intercept it before it leaves the atmosphere. And anybody that's done public speaking knows that 60 seconds is quite a long time. And I've modeled the standard missile 6, which is the newest version from Raytheon. It's a 6.5-meter missile. It has 2 stages, and it's capable of reaching, the unclassed sources say it's capable of reaching Mach 3+. So what I've done is I have assumed the fuel potency and ISP weights to get me to just about 3.5 kilometers per second in a reasonable time period by the end of the boost phase. And you can see that afterwards the drag and gravitational effects slow it down considerably. Well, the current guidance laws that are in effect right now can be really broken into 2 categories. There's the completely unacceptable guidance laws, such as pure pursuit or beam rider, which point the velocity of the missile at the target. They don't lead the target. They don't in any way. So they're very capable of achieving interception with targets that don't move very fast. such as ground clutter tanks, that sort of thing. Those are not even remotely acceptable for this particular application. Well, the other family is the proportional navigation and all of its derivatives. These guidance laws are used in almost every tactical system in existence today, and there's a reason. They're very good at intercepting fast targets. They point the differential velocity vector at the target, so basically they lead the target and they line up an intercept in front of the target, and that allows them to overcome the speed and the maneuvering of the target. The problem is it still has three fatal characteristics that go into that affect us in the ballistic missile. One is the control system time constant. They only use current data. They know where the target is, they know where the target is accelerating, and they predict, and they don't predict an endpoint, they just kind of try to drive that error to zero. Well, the amount of time it takes the mechanical system to implement that command is a specific amount of time, and that's characterized by the time constant. And there's the technological limitations, the physical limitations, mean that can only go so small. But with the speeds and the errors that we're talking about, those can become fairly large. So that's something that will overcome. The second one is the endgame environment. The missile doesn't know where it's going to finally be when it intercepts the missile, or intercepts the target. It could be out of the atmosphere, it could be anywhere. The missile just doesn't really care. The point is to try and fly a straight line path to minimize the maneuverability, and in the hopes that you're going to be in an advantageous area when you get there. But it doesn't take into account that particular aspect. And then finally, the interception geometry, which is purely the result of the geometry of the launch. The missile was launched in front of or behind the target, the speeds of the two, and the relative maneuvers involved. It doesn't take into account, it doesn't say I want to hit it at a 90-degree angle, I want to hit it in the front or in the back. It's purely the physics of the situation. It's an output of the system, not an input to the system. And these are three characteristics that my new algorithm can overcome. To start with, we did some modeling of the proportional navigation family using augmented proportional navigation, which is a specific version of the guidance law. We developed a 3-degree of freedom model, and we also developed a 6-degree of freedom model, and some simulations to allow us to see the impact angles, to see the amount of relative kinetic energy, and the miss distances available. And I've shown just a brief portion of them here, but what we came to the conclusion was that the augmented proportional navigation is not sufficiently robust in this particular area to be able to be used effectively.